Hi, in this video we will examine how we can send and receive Manchester encoded bit streams using AVR microcontrollers. The fundamental principles of Manchester encoding will be covered first, before we move on to discuss different ways to implement encoding and decoding. We will see that the core-independent peripherals allow us to make efficient solutions with very high baud rates. Serial data can be represented in many different ways in digital communication. One of the more common encoding schemes, called non-return to zero, involves using low voltages to represent the value 0 and high voltages to represent the value 1. A problem with this approach is that long sequences of ones or zeros are represented by a constant voltage. The receiver can then easily fall out of sync with the transmitter. This encoding scheme therefore often necessitates an extra communication channel to enable the transmitter to share its clock with the receiver. In the Manchester encoding scheme, both the data and the clock are included on the same channel. Instead of representing zeros and ones as constant voltages, we use the transition from low to high voltage to represent 0 and the transition from high to low voltage to represent 1. Here is an example showing the same bit sequence represented in both encoding schemes. If we compare the Manchester encoded signal with the clock signal used with the NRC encoding, we see that the Manchester encoded signal always has a transition when the clock has a rising edge. The clock signal can therefore be extracted from the Manchester encoded signal. Note also that we can generate the Manchester encoded signal by performing a logical exclusive OR operation on the NRC and clock signals, which we will use shortly. Let us now take a look at how we can implement Manchester encoding using the AVR microcontrollers. We have made two different implementations to illustrate how much can be gained from using the core-independent peripherals. The first and most straightforward implementation uses a timer counter B peripheral to generate periodic interrupts. Each time an interrupt is triggered, the core analyzes the data to be sent and determines whether or not we should toggle the output pin. This core processing takes some time and must be conducted twice for each bit period. This reduces the maximum supported baud rate. Better baud rates can be achieved by using the core-independent peripherals. In this implementation, we use the logical exclusive OR relation between the Manchester encoded signal and the NRC and clock signals. We input our data to the USART peripheral, which generates both an NRC encoded signal and a clock signal. These are then sent to the custom configurable logic block that functions as a logical exclusive OR. The result, as we saw previously, is the Manchester encoded signal. Since we can transfer 8 bits to the USART at once, and since half of the transitions are clock transitions handled by the CCL, this implementation reduces the number of interrupts per time that the core must handle by a factor of 16, relative to the core-based implementation on the left. The maximum baud rate should therefore be about 16 times higher using this solution. Now, let us move on to decoding. We have made two different implementations here as well. The first implementation uses a timer counter peripheral to measure the time between each signal edge. From this we can recreate the Manchester encoded data, provided that we perform some time-consuming calculations using the core. Due to the time spent processing interrupts and data, the supported baud rate is not that high. A much more sophisticated implementation is possible if we employ a wide range of core-independent peripherals. The fundamental idea behind this second implementation is that we want to avoid reading every single bit using core processing. Instead, we can use the serial peripheral interface, which can read and store 8 bits before it is necessary to trigger an interrupt. The SPI, however, cannot read Manchester encoded data directly. It also requires a clock signal to know when to sample the received signal. We therefore use the following setup to extract a clock signal and a NRC signal from the Manchester encoded signal. The CCL is here configured to function as the D flip-flop and the exclusive OR block. The delay circuit is constructed using a combination of CCL and timer counter peripherals and allow us to utilize a powerful property of the Manchester encoded signal. namely that the NRC signal can be recovered by sampling a quarter period before the clock's rising edge. Using this setup, we can then construct a solution that uses the SPI to read and store 8 bits at a time before an interrupt is triggered. Here is a schematic showing how the different peripherals are connected in this implementation. It is more complex than its core-based counterpart, but it supports much higher baud rates, as we shall see promptly. Let us now compare the performance of the different implementations. The maximum baud rate when using the core-based encoder and decoder is about 75 kilobaud. The CIP-based implementation, on the other hand, supports up to 1350 kilobaud. That is an 18 times higher baud rate and illustrates the power of the core-independent peripherals. In addition to superior baud rate, the waveform quality is also better for the CIP encoder than for the core-based encoder. Here are some examples of 50 kilobaud waveforms generated by the two encoders. The numbers indicate the time between edges in microseconds. The core-based encoder gives a quite irregular waveform, while the CIP-based encoder produces a waveform of much better regularity and quality overall. The irregularity of the waveform from the core-based encoder is highly dependent on the baud rate, and becomes progressively worse as the baud rate is increased, and conversely the waveform is more regular for lower baud rates. The CIP encoder maintains a very high waveform quality and regularity even for very high baud rates. To summarize, the core-independent peripherals has allowed us to make solutions that have much higher baud rates and better waveform quality, and that also leaves more capacity for data processing and other calculations. The core-based solution might be sufficient for some low baud rate applications, but the CIP solutions are much better overall. All implementations of the Manchester encoders and decoders we have discussed in this video are available for download through Atmel Start. Please see the video description for further details. We hope that you have enjoyed this video and that the core-independent peripherals can help take your own projects to the next level.